Okay, so this video is going to be kind of like an introduction to topic 7.3. The name of topic 7.3 is called the structure of matter, but a lot of this unit is going to be about what I like to call particle physics. Now, there's something important that you need to know about topic 7.3. This is kind of a specialized topic in the IB core curriculum, and when I say that, what I mean is most of the topics we learn about in IB physics, like mechanics, thermal physics, waves, electricity, and stuff, those are all topics that are commonly taught in other physics courses, AP physics or college level physics. But a lot of the concepts that we're going to be talking about in topic 7.3 involves things that are not really taught at the high school level, and in a lot of cases are not even taught at the undergrad level in college. And so a lot of these concepts are things that even though I have my degree in physics, are things I did not learn about myself in college because they're normally taught at the graduate level. Okay, so when I say that, what I mean is that the very, very best resource for this topic is going to be your IB physics textbook. Okay, because this is such a specialized field of study, it's really only taught by the IB curriculum at the high school level. That's going to be your best resource for studying this. It's going to be really difficult to find outside resources for this unit, although I do encourage you to try. Okay, so again, I would highly encourage you to spend a lot of time reading your IB physics textbook and doing the problems that you find in there. Okay, so topic 7.3, again, is called Structure of Matter. This is going to be the last unit in atomic and nuclear physics, and then after this we will be moving on to a different unit. This unit, while short, contains some very strange and abstract concepts. In some ways it's very interesting, and in some ways it's going to be a little confusing and difficult to follow. I will do my very best to explain everything to the best of my ability, but again, for this particular subject, we are dealing with things that I myself did not even learn in college, and so I kind of had to teach myself this topic from the IB physics textbook. So again, that is definitely going to be your #1 resource for learning this material. This unit has to do with more modern physics. Typically, modern physics refers to physics after around the 1910s and the 1920s, after Rutherford came up with his model of the atom. And it's a continually growing area of physics. And so, unlike a lot of things we study in physics, this is actually something that we are still learning about. Our knowledge in this topic is still incomplete. And so it is kind of interesting in the sense that this is an ongoing field of study. And, if you were to go to college and get your physics degree in a few years, you could be adding to this field of study. So, let's talk a little bit about the understandings in 7.3. Okay, so just to give you a taste for some of the things we will be talking about in 7.3, we are going to talk about quarks, leptons, and their antiparticles. If those words don't mean anything to you, they will later on. We're going to talk about hadrons, baryons, and mesons. As we'll see later, baryons and mesons are types of particles called hadrons. We'll be talking about new conservation laws, the conservation of charge, the conservation of baryon number, lepton number, and something called strangeness. The nature and range of the strong nuclear force, weak nuclear force, and the electromagnetic force. Now, those forces we have referenced before. We'll go into a little bit more detail about those. Exchange particles, Feynman diagrams, confinement, and the Higgs boson. Okay, so a lot of interesting stuff in here that we will get to in 7.3. And if you don't know what quarks and leptons are, those are types of particles. And again, we'll talk about that later on. Now, what must you be able to do at the end of 7.3? The first bullet point we actually kind of cover in IB Physics 1. The first bullet point says, describing the Rutherford-Geiger-Marsden experiment that led to the discovery of the nucleus. Okay, so even at this point, after having taken IB Physics 1, you should be able to do that. You should be able to explain the results of the Geiger-Marsden experiment, the gold foil experiment that led to the discovery of the nucleus. Okay, the other things you need to be able to do are apply conservation laws in particle reactions. Okay, we'll spend lots of time doing that. Describe protons and neutrons in terms of quarks. That's not difficult at all. We'll talk about that later on. Comparing the interaction strength of the fundamental forces, including gravity. We briefly mentioned that when we did topic 7.1 last year. So that's something we'll mention again, describing the mediation of the fundamental forces through exchange particles, and then sketching and interpreting simple Feynman diagrams. And that's probably one of the most difficult things in this topic. And it's not that it's really difficult so far, or to be fair, but it's kind of weird and abstract, and takes a while to get your mind wrapped around. And luckily, the IB curriculum keeps things as basic as they possibly can, and so I would say, again, studying your IB textbook is really going to help, because there's a limit to how many different problems they can give you, because this field of study is not normally taught at the high school level. Okay, so again, your IB physics textbook is a wonderful resource for this topic. Okay, now just to kind of tease you as we lead into this, I have a few videos I want you to watch about why particle physics matters, because this is one of those fields of study where it's not necessarily obvious why it is that we're studying this. Okay, now there are some practical applications with particle physics. As you can see on the slide, the development of this field has led to technological advances in other areas. Okay, for example, in medicine, okay, there's lots of different types of radiation therapies that you can apply to cancer and other diseases. A lot of our scanning technologies, MRIs, PET scans, things of that nature, involve or kind of developed as our understanding of particle physics grew. And then, of course, semiconductor technology, which is the basis behind all modern electronic devices, computers, cell phones, smartphones, Apple Watches, any modern smart device. We only have those devices because our research into this field of study kind of led to better semiconductor technology. Okay, and if that doesn't do it for you, I will also leave you with this quote. It says, "The scientist does not study nature because it is useful. He studies it because he delights in it, and he delights in it because it is beautiful. If nature were not beautiful, it would not be worth knowing, and if nature were not worth knowing, life would not be worth living." Okay, so in other words, in some respects, particle physics is worth studying just because it deepens our knowledge of the universe, and sometimes that is its own reward, even without any practical applications. So I'm going to link these two videos up. I would encourage you to check those out, and there's one more video I want you to see later on. Just really quickly, last year we talked about how Thomson discovered the electron. He did that in the late 1800s. We're not going to get into exactly how he did that, but basically after he discovered the electron, he came up with a model of the atom, which was the plum pudding model, or the Thomson model. And in the Thomson model, remember, you basically have like a spherical atom, and you have these electrons embedded in the atom, kind of like, seeds in a watermelon, surrounded by a fleshy, positive-y, soupy type of substance. Remember, this is before we knew protons even existed. And so Thomson's model, of course, was disproved by the Geiger-Marson experiment, after which Rutherford came up with a new model of the atom, which contained the nucleus, okay, that small, dense, positively charged center of the atom. And he did so in the 1910s, which also later that decade, fun fact, he also discovered the first example of artificial transmutation. So Rutherford was definitely a busy guy during that decade. Okay, now, what we're going to do is kind of fast forward a little bit. At the time of Rutherford, where we're going to stop for a second, in the time when he came up with this new model of the atom, he knew about the nucleus, but he didn't know that protons or neutrons existed yet. Okay, so all we knew at this point was there is a small positively charged dense center of the atom, and we knew about electrons. Okay, and that was basically it. Okay, and over time, our knowledge and understanding of what the smallest particles in the universe are has increased. Okay, thousands of years ago, Greek philosophers hypothesized the existence of the atom, okay, meaning indivisible, meaning theoretically the atom by its very name should be the smallest piece of matter. And then Rutherford came up, or not came up, with the idea of the nucleus. He discovered evidence for the nucleus based off of the Geiger-Marson experiment. But the nucleus, based off of his calculations, was tens of thousands times smaller than the atom. And then a few years later, the proton was discovered that was even smaller, and the electron was eventually shown to have an even smaller size. And over time, our knowledge of what the smallest particle in the universe has definitely changed as we get better and better experimental evidence. So we are going to skip ahead a little bit and talk about a discovery made in the late 1920s by a guy named Dirac. Dirac was kind of a combination mathematician and physicist and super smart guy. And basically, with all of his math skills, he basically mathematically predicted the existence of an antiparticle, okay, an antiparticle to the electron, and which we later called the positron. Positron meaning positive electron. Okay, and hopefully that name sounds familiar. Later, we figured out that this mysterious beta minus particle was an electron, and the daughter to that, the beta plus particle, was what we now call a positron. Okay, now the way he did that is really complicated, and I'm not sure I fully understand it, but my understanding is that the analogy to how he predicted the existence of this antiparticle was basically kind of like how when you take a square root of a number, you get a plus answer and a minus answer, okay, a positive answer and a negative answer. And without getting into what equation he was dealing with, my understanding is that's basically how he came up with the idea of this antiparticle. Now, when I say an antiparticle to the electron, a lot of people think that the proton is the opposite of the electron, but that's not true at all. In fact, the proton is thousands and thousands of times more massive than the electron. Now, it is true that one is positive and the other is negative, and they have the same size of charge, except one is positive and one is negative. But besides that, they're completely different. Okay, so when we say an antiparticle to the electron, what we mean, at least just for now, is we mean a particle that has the exact same size and the exact same mass and the exact same everything as an electron, except it happens to be positive. Okay, and that is what we call the antiparticle to the electron, aka the positron. And this was the first discovery of what is more generally called antimatter. And so if you've ever heard of antimatter before, a positron is an antiparticle. That would be an example of that. So Dirac mathematically predicted this without any experimental evidence in 1928, and a few years later, this other physicist named Anderson discovered evidence for the positron in cosmic rays. And down here I basically talk about antiparticles. Now, when two antiparticles meet, let's just say, for example, if an electron and positron were to meet, they cause what's called annihilation. That is the actual technical term. They annihilate each other. They completely destroy each other. They cancel each other's existence out, and all the mass that was there before is converted into energy, because remember, E equals mc squared, and mass can turn into energy and vice versa. Okay, so if an electron and a positron were to meet, they would basically create two photons that carries away their mass that's been converted to pure energy. Okay, and again, that's called annihilation. We'll talk more about that later, but that's a really interesting property of antimatter. Now you might ask, why doesn't the whole universe blow up then if there's like matter and antimatter? And the answer is, for some reason that we still don't know the answer to, when the universe was formed, there was more matter than antimatter. And so it's not a 50-50 split, at least not in our universe. And so our universe is dominated by normal matter and not antimatter. And the reason for that is still kind of not known. But, you know, people are still trying to figure out why that is exactly. The opposite of this effect, this annihilation, is something called pair production, where basically you have two photons out there and they just kind of poof away, and their energy spontaneously turns into a particle and an antiparticle, which is also kind of strange. So if you've ever heard of antimatter, if you've ever watched Star Trek and they talk about antimatter, you know, which powers the warp reactor or the warp drive in Star Trek, that's what they're talking about. Basically, the idea behind that is, you know, if you get a bunch of matter and antimatter and you mix them together, it creates a lot of energy because all of that mass is turned into energy, and then you can use that to power like spaceships and stuff, which is theoretically possible, maybe. That's obviously something that we're not even close to being able to do, but it could technically maybe happen. I don't know about the faster than light speed travel, but at least in theory, we could use matter and antimatter as a source if we could figure out how to collect antimatter, which is kind of difficult to do because, you know, antimatter, when it collides with matter kind of disintegrates. So anyway, just a few more things and then we will stop this video. Okay, so you might ask, how in the 1820s and the 1830s, how did they discover antiparticles? Like, how is that even possible? And the way they did that, or one of the ways they did that, is using what's called a cloud chamber. Okay, and a cloud chamber is basically a box that has, for lack of a better term, a cloud in it. It has, water droplets suspended in the air. And these particles, like protons and electrons and positrons, when they go through the air, they ionize, or they cause ionization, and it causes the water molecules to kind of coalesce around where the path of those particles is, and it forms tracks in the clouds. And so you can actually see these invisible particles because they make tracks in the clouds. And I'll show you, or I will put up a link to a video that I want you to see, where you can actually see different radioactive sources emitting their radiation because of the effect they have on a cloud chamber. And basically, at one point, somebody sat down to do an experiment and looked in the cloud chamber, and they saw these two paths in the cloud. They saw these two circular tracks, and by measuring the size and the radius of one of the tracks, I should, by the way, say that the reason the tracks are circles is because there's a magnetic field around the box. And charged particles, we'll talk about this later this year, but charged particles, when you put a charged particle in a magnetic field, it makes it spin in a circle. And so basically, by measuring the magnetic field and measuring the radius of the top path, knowing about centripetal force and all that stuff, you can figure out that, hey, this top path is an electron, because the particle that causes this green track that's on top has the same mass as an electron, so it must be an electron. And then they notice that, hey, there's another track going the opposite way with the exact same size, but in the opposite direction. Okay, that means that particle must have the same mass as the electron, but with an opposite charge, because it's going the opposite way in a magnetic field. Okay, and so that's kind of experimentally how they discovered the positron way back when. Okay, so we will talk more about the different types of particles that were discovered and how they are now classified in the next video. I am going to put a link up to a video I want you to see at least the first 5 minutes, because it's really cool, where you can actually see a cloud chamber in action. But that's just kind of like a little teaser into 7.3 and some of the interesting things that we will be talking about. So, as always, please let me know if you have any questions, and I will see you guys in the next video.